Good evening, my name is JMcCulloch, and this presentation is on AC to DC full wave rectifier circuit analysis. This is in regards to EC 331, 311, and 341, which I will discuss each part of the circuit in terms of each of those classes throughout this presentation. The basic idea is that you have an input, you have a system that creates an output from that input. And what we're talking about is we're taking a sine wave, an AC circuit, and we're trying to create a DC voltage from it in order to power our different electronic devices. This is the basis of everything that we do electronically. So the circuit that we are looking at is a full wave rectifier, which is taking, like I said, the AC input and creating a DC output. Our input signal is a sine wave that goes through the bridge rectifier. The bridge rectifier is taking the sinusoidal wave and creating a rectified or just the magnitude of that signal, which means basically you're taking the entire sine wave and everything that's negative, you're flipping it onto a positive. This is now the input to the rest of the system, which is an RC circuit. The whole purpose of the RC circuit is to smooth out the signal in order to have a DC voltage or an approximation of a DC voltage. All right, next. So this is the input of the system, which is a sine wave. Now, to prove that to figure out whether or not the system is linear and time invariant, which are two properties which we need in order to be able to do a proper analysis of the system, are the linearity and the time invariance. So, in order to demonstrate time invariance, you simply need to show that the signal that you are putting in is going to be the same as the signal that is coming out. So in this, what we've done is we've taken just the sine input and we've scaled it. We've multiplied it by a scalar. This is checking for homogeneity. And then we've shifted in order to determine whether or not the system is time invariant. Now, the bridge rectifier takes that sine wave, which we can either scale up or shift, and it will create this rectified or the magnitude of the sine wave signal. This signal is what is going to be pushed through the RC circuit in order to create the DC voltage. Now, before we get there, the sine wave has this full magnitude. So this is the ideal input. So once that input signal goes through the bridge rectifier, this is just a diagram of the half wave, not the full wave. It's 0 when the sine wave is in its negative cycle. And this little gap right here is the voltage difference or the voltage drop over the diodes. In our case, in the bridge rectifier, each section has 2 diodes, so this gap is 2 VD, 2 voltage over the diode. And this follows that all the way through. This is just for the rectifier, for the half wave. But what happens in our case is a full wave, so when we flip this up, it not only takes this part, but it also is taking the voltage across the negative portion. So this part right here is the rectifier. That is the voltage directly after the diode bridge. That is the voltage that is going to be charging up the capacitor that will be used to smooth out the signal. So this difference right here is, if you look, we'll look back at our circuit diagram, the resistor before we get to the capacitor, R1, has a voltage drop across it, which is the current times that resistor. So that's the difference between here and there. So this is V out, which is the voltage across the capacitor and the resistor that's in parallel with it. When V rectifier is following the sine wave, the V out is still directly proportional to it. But just because V rectifier begins to decrease does not mean that the capacitor is going to discharge, because the voltage of V rectifier is still greater than the voltage of V out. Until we get to this point, which is when V rectifier equals V out. And at that point, there will be no current going through R1, which means V out equals V rectifier. So these two graphs become the same voltage until we get to this corresponding VD on portion of the next period. And at that point, the same thing happens here. We now have current going through that first resistor, which is why there's still that difference, and the same thing happens all the way through. Now, what happens is we're taking, to find the actual DC voltage, it is the average between the trough and the peak all the way through here of V out. And that is how it's basically smoothed out. Because if we didn't do that, then every cycle of the rectified signal would basically turn off your devices, which that's almost useless. In terms of the electromagnetics, the diode is made up of a p-n junction, which is either an excess of electrons or an excess of holes or protons, not quite. The buildup of the electrons on the p side and the holes on the inside is due to hole and electron diffusion, which this depletion region is built up of oppositely charged particles from what P and N are. So this is actually full of holes, and this is actually full of electrons, but in this region, they are attracted, which creates this difference in charge. Now, the charge density switches, and whenever you have a difference in charge, you are now creating a voltage. Well, you're creating an electric field. So the electric field is represented by this graph. Now, anytime that you have an electric field or a field of any sort, you are creating a force. And that force is opposing the current and the voltage going across that diode. That is where VD on goes to in terms of the power management system. So when you are dealing with the total system, you have to account for the loss of voltage across each of those diodes, no matter what. And that concludes my presentation.